Okay, so with 4.4, we're really going to get more into center and variability in normal distributions. You may have seen some of this already. The first one is called Chebyshev's rule. So Chebyshev. Chebyshev rule states that for any distribution, the proportion of observations that are within k standard deviations is at least 1 minus 1 over k squared. So if I'm looking at what proportion of data should be within 2 standard deviations of the mean, I would do 1 minus 1 over 2 squared, so 1 minus a fourth, so 3/4, so about 75% of my data, which is sort of what we had at that last example yesterday. For 3 standard deviations, 1 minus a ninth, 8/9 is about 89%. 1 minus 4 would be 1 minus 1/16, so 15/16, so about 93.75%. So suppose the distribution of incomes for baseball players have a mean of 2.6 million and standard deviation of $5.1 million. At least 75% of the players will have incomes between two values. So I want 2 standard deviations. So I'm going to do 2.6 minus 2 standard deviations and 2.6 plus 2 standard deviations. So with the minus, I end up with negative 7.6. Here I get 12.8. Now obviously you can't make negative amount of money, so we're going to say it would be from 0 to 12.8 million. Now the problem is Chebyshev's rule works for all distributions, but it usually underestimates the proportion of data within each set of boundaries. So we honestly do not use it that often. Most of the time, we don't use it. Unless it's specifically asked for it, we usually use what the next one is, which is the 68, 95, 99.7 rule. Sometimes you'll hear it called the empirical rule. States that if the data set can be well approximated by a normal curve, so it's got to be a normal curve, what that means is 68% of your data is within 1 standard deviation of the mean, and then 95% of your data is within 2 standard deviations of the mean, and 99.7% of your data is within 3 standard deviations of the mean. So, in a normal curve, we call it the bell curve sometimes, it's a single-peaked, symmetrical, and mound-shaped. To identify 1 standard deviation from the mean, we find the inflection points. Now, calculus students, don't freak out. All we're going to do is estimate it. So usually we have 3 lines on either side. So this is your x bar. Okay, and then this is x bar plus s, x bar plus 2s, x bar plus 3s, x bar minus s, x bar minus 2s, x bar minus 3s. So it says 68% should be within 1 standard deviation. So that means it's above or below. So really what that means is you have breakdown of 34%, 34%. Okay. Now, we're going to break down each one of these. 95 is within 2. So if I do 95 minus 68, I get 27. Cut in half, I get 13.5. So there's 13.5% in each one of these bars. Okay, that's the amount of data. Then, if I do 99.7 minus 95, I get 4.7, so 2.35. So in here it's 2.35, 2.35. Now, you still have leftovers, right? You have 0.03 left over. So divided by, you have 0.3, not 0.03. You get 0.15. So 0.15, 0.15. So you need to know this breakdown. You can easily Google it. Just put bell curve, normal curve, and it'll come up. We're going to do some examples on the next page. But you need to know it. If you don't know it, you can do what I just did. Or really, it's symmetrical. It's kind of like a unit circle. You've memorized the top half. The bottom half is just the other side. So let's try an example on the next page. Okay, so what I like to do on this one, I like to draw the whole thing out, especially when I'm going to answer like a ton of questions like this one. So off to the side, I'm going to do a little mini normal distribution. And it doesn't have to be perfect. So here, the heights of the students are approximately normal, with a mean of 66 and a standard deviation of 3. So your mean here is 66. So 69, 72, 75, 63, 60, 57. So again, you have 34, 13.5, 2.35, 0.15. Okay. So now that we have this, this will be a whole lot easier. So I'm just going to leave it off to the side so you can still see it. Approximately 95% of the heights will be within which two values? So again, that's 2 standard deviations. So it should be between 60 inches and 72 inches. So our 2 standard deviations. What proportion of students will have heights between 63 and 69? So 63 and 69 is just 1 standard deviation. You can add together the different bars, so you get 68%. So 68% of all students should be within 63 to 69 inches. What proportion of students will have heights between 63 and 72? So now I'm just going to add up all 3 of these bars. 34, 34, and 13.5. So 81.5%. What proportion of students will have between 57 and 69? So I'm going to add up all 4 of those bars. So 34, 34, 13.5, and 2.35. So 83.85%. What proportion of students will have heights greater than 72? So 72 is here. Greater than, I'm going to add these 2 together. So 2.35 plus 0.15, so 2.5%. So see how easy it was now that we had this all worked out? You just had to count. So just a few things. The empirical rule only works for distributions that are normal. It's very rare that an observation to be more than 3 standard deviations from the mean in a distribution that's already normal. So the other way you can use the normal distribution is with measures of location. So suppose a professional soccer team has the money to send 1 additional player, and they're considering either adding a goalie or a forward. The goalie has a 70% save percentage and the forward averages 1.2 goals per game. In the league, the average goalie saves 86% of the shots with a standard deviation of 5. The average forward scores 0.9 goals per game with a standard deviation of 0.2. Who is better at this position? The goalie is 4% higher than average, but the forward is only 0.3 goals higher than average. But we're comparing different units, so we can't just say 4 is better than 0.3. We want to figure out where they fall within each of their respective distributions. So this is where this thing comes in handy that we will use for the rest of the year, called a standard score or a z-score. So a standard score or a z-score z is equal to x minus x bar divided by s. And this is not on your formula sheet, so you do need to know it. But it's how many standard deviations you are above or below the mean. So for the goalie, his z-score, he saves 90%. The average in the league is 86% save with a 5% standard deviation. So he's 0.8. So he's 0.8 standard deviations above the mean. Now your forward, his z-score, he averages 1.2 goals per game. League averages 0.9 with 0.2. So that's 1.5. So he's 1.5 standard deviations above the mean. Okay, so using standardized scores have different advantages. Since z-scores have no units, we can compare values that are measured on different scales with different units or different populations. So here, I'd probably want to pick the forward because he actually does better. His z-score is higher than the goalie's z-score. So you're comparing two different distributions. So the next thing is another example. Suppose that the distribution of male heights has a mean of 69 inches, a standard deviation of 3, and female heights has a mean of 64 inches with a standard deviation of 2.5. So who is taller relatively speaking, a 72-inch male or 67-inch female? So again, we're going to find their z-scores. So for the guy, I'm going to take 72 minus 69 divided by 3, and I end up with 1. For the female, her z-score, 67 minus 64 divided by 2.5 is 1.2. So the female is taller. She is 1.2 standard deviations above the mean for females. The male is only 1 standard deviation above the male mean. So z-scores don't have units. It just tells you how far above or below the mean you are. So that's how I usually memorize the formula, because it's always your number first minus the mean divided by standard deviation. An exclusive club only allows members who are especially tall. The height requirement for women is 72 inches. What is the equivalent height requirement for men? So what we're going to do, we're going to find the z-score, and then we're going to convert it for the guys. So for women, my z-score for this club is 72 minus 64 divided by 2.5. So I get 3.2. So you have to be 3.2 standard deviations above the mean or more to get into this club. So now we're going to convert it for the males. So I'm going to make 3.2 equal to x minus 69 divided by 3. So you got to do some algebra. I know it's been a minute, but I'm sure you can do it. So I'm going to do 3.2 times 3, so 9.6, x minus 69, so I'm going to add. So I need to be 78.6 inches or more for the guys. So you can easily convert from one z-score to another, since it's just a standardized score. So here, males have to be 78.6 inches or taller. A new male student is 66 inches tall. What percentile is his height? Okay, so percentile, remember, is the percent less than him. So we need to figure out the percentage. So let's find his z-score. So 66 minus 69 divided by 3. You get a negative z-score. That's okay. That just means he's below the average. So if you think about our normal distribution from before, all it is, if the mean is here, that means you have a z-score of 0 if you're on the mean. Then you have 1, 2, 3, negative 1, negative 2, negative 3. So like that 34, 34, that 13.5, 2.35, and 0.15. It all works out the same. So z-score, the standard one, you just start at 0 and plus 3 to minus 3. So if he's at negative 1, this is where he is. I want the percent less than him. I'm going to add up all three of these. So 2.35, 0.15, and 13.5 gives me 16. So he's the 16th percentile. And we'll get in more in depth in the normal distribution in chapter 7. For now, you just need to know like the big, what happens, like if they land at 3.2, we wouldn't be able to find that percentile. We'll do that later. For now, just know like the nice whole numbers.